Okay, so here is our review for test 1 for dynamics. So here's this first problem. So a particle is moving along a straight line such that when it is at the origin it has a velocity of 4 meters per second. If it begins to decelerate at a rate of, acceleration is negative 1.5 v to the 1/2, determine the distance it travels before it stops. If you're not sure where to go, just kind of rewrite what is given. What does the problem statement tell us? So given is, the velocity is 4 meters per second at the origin, and it begins to decelerate. So acceleration is negative 1.5 v to the 1/2, and I'm looking for, so find the distance it travels before it stops. The distance it travels before it stops. Okay, so this is one of those problems where acceleration is given in terms of velocity, and we want to find distance, or we want to find position. Right? How do we handle a problem where acceleration is given in terms of velocity? Well, let's look at our equation sheet. So here's our equation sheet. First thing I would do on your test is tear this last page of the test off. Last page is our formula sheet. Tear that off, put it beside you so you can work this problem out with your formula sheet right beside you. So if I have acceleration in terms of velocity, how do I handle that? Well, let me see here. I know how to handle if acceleration is in terms of time. Right here, if acceleration is in terms of time, I know how to handle that. If acceleration was in terms of s, I know how to handle that. But if acceleration is in terms of v, what do I need to do? I need to either maybe divide this one over to the other side or divide this one over to the other side. All right, so which one do I use? Well, is the problem asking for, or is it giving me t, or is it asking for and giving me s? That's kind of what I need to look at. So for this one, it tells me, it doesn't say anything about time, it's asking about position. So this last equation right here, v dv is equal to ads is the one I'm going to use. All right, so let me use that one. All right. So I know that integral of v dv equals the integral of a ds. So I'm going to divide the a to the other side. So integral of v over a dv is equal to the integral of ds. And so v over a would be integral of v over negative 1.5 v to the 1/2 dv is equal to the integral of ds. And so this, on the left-hand side, I'm just going to rewrite this. Not going to do the integral yet. Negative 0.6, let's see, negative 0.667 v to the 1/2, right? Because I have v to the 1 on top, v to the 1/2 on bottom. We're left with v to the 1/2. All right, so that is my integral. So the integral of that, right there, would be, the way I like to do it, v, add 1 to the exponent, so we're at 3/2, divide it by the new exponent, and I still have negative 0.667 not dv anymore, because I've already done the integral, but I do need to evaluate this from v initial and v final. And here this would be s, from s initial to s final. So doing this integral, what is my initial velocity, what is my final velocity, what is my initial position, what's my final position? So if I started at 0 and I started with a velocity of 4 meters per second. And so I'm ending at some s final, which I don't know. But, what did the problem statement say? The problem statement said, find the distance it travels before it stops. Well, when it stops, it has a velocity final of 0. So here I'm going from 4 to 0, from 0 to SF. All right, so I'll just continue here. Plugging in 0 for everything minus when I plug in 4, negative 0.667 times 4 to the 3/2 over 3/2 is equal to SF minus 0. So really SF, and really that's the distance that we're looking for. So if we just do this math, let's see, if we just did this math, we would be left with SF is equal to 3.55 meters. And so that is, if we started at 0, that is the distance d that we traveled. All right, so let's look at this problem. It's a projectile problem. Projectile problems definitely a big part of this class. Definitely will show up on the test. Okay, so measurements of a shot recorded on videotape during a basketball game are shown. Ball passes through the hoop, so it goes from A to C, even though it barely clears the hands of player B who attempted to block it. So neglecting the size of the ball, determine the magnitude of VA of its initial velocity and the height of the ball when it passes over player B. All right, so projectile problem. But this one kind of has a point A, a point B, and a point C. So, we could do a projectile from A to B, or maybe A to C. We could even do it from B to C. Different points, you can do your problem, starting and ending at different points. So I want to know H and I want to know VA. So my initial thought is, well, let's go from A to B. But if I went from A to B, then I would have too many unknowns. If I went from A to B, I don't know VA. Let's see. I don't know VA, and I don't know H, and I don't know time. Time is what we use a lot in these problems. But let me think about it. If I went from A to C, then I think about my unknowns going from A to C. I don't know VA, but I do know that the height is 10. I don't know T. So going from A to C, we only have 2 unknowns, and we can solve for those 2 unknowns. Remember, for projectiles, we kind of separate x and separate y. So we have an equation for x and an equation for y. We have 2 equations. We can probably solve for those 2 unknowns. So my kind of roadmap for this problem is, let me go from A to C and solve for these 2 unknowns. And then let me plug in the VA that I find, plug this VA in, not the T is different, but plug this VA in over here, and then I'm going to redo a projectile problem from A to B. Now that I know VA, then I'll have 2 unknowns, H and T. So let's try that. So I'm going to go from A to C. All right, so going from A to C. And, projectile problem, I like to separate X and Y. So I'm going to kind of separate X from Y. Maybe let me keep that in view. So let me kind of plug in my X values over here, plug in my Y values. You may want to go ahead and start with your equation. Sometimes I like to kind of rewrite what I know in the X direction, what I know in the Y direction. So in the X direction, let me think about its position in X. So again, this is my X direction position. It starts at 0 and it goes to 30. All right, I'm going from A to C. Its initial velocity in the X would be VA cosine 30, right? It's at 30 degrees, whereas my initial velocity in the Y would be VA sine 30. My acceleration in the X is 0 for these projectile problems. whereas the acceleration in the y would be down 9.81 if we were in meters per second, but let's look carefully. We are in feet, so that would be down 32.2 feet per second squared. Okay, and kind of going back to my y, let me see my initial and my final y. Again, y, I need to be consistent. Am I calling up positive? I'm going to call up positive, yes. And so initially, I started at 7 feet, right? Initially, I'm right here. And final, I ended at 10 feet, positive 10 feet. So I am calling the ground my 0 height. All right, so I started at positive 7. I ended at positive 10. What else do I know, or maybe I don't know? I don't know the time, but I do know that the time in the x direction is the same as the time in the y direction. So I just kind of rewrote everything I knew. Let me use my equation. So for both of these, it is a constant acceleration, right? In the x direction, it's constant acceleration, 0. In the y direction, it's constant acceleration of that 32.2 feet per second squared down. So let me look at my equation sheet. All right, here's my equation sheet, and I could kind of look at my knowns and unknowns, look at what I'm given, what I'm looking for. Almost every time for these projectile problems, we're going to use this third and final constant acceleration equation. Remember, these are the constant acceleration equations right there. I'm going to use that last one both in the x direction and in the y direction. So let me do that. All right, S final is equal to S initial plus VIT plus 1/2 AT squared. So this is in the x direction. It ends at 30. It started at a height of 0. It started with an initial velocity of VA cosine 30. All right, multiply that times t. And then acceleration is 0. So that's my equation in the x direction. I have an unknown VA and an unknown t. Can't really solve for that, but maybe I can do a little bit of math and rewrite that as much as I can. I'm going to say VA, I'm going to write one variable in terms of the other. VA is equal to 30 over cosine 30 times t. All right, let me go to the y direction. The y direction, SF equals SI plus VIT plus 1/2 AT squared. Okay, it ends at 10. Started at 7. Started with a positive, right? This velocity was up, so it's positive velocity of VA sine 30. Don't forget to multiply it times t. A lot of people forget that t. And then plus 1/2, its acceleration, negative 32.2 t squared. So this y equation, I also have two unknowns, VA and t. So two equations, right? One equation right here, one equation right here, and two unknowns. So write one in terms of the other. Plug this in right there for VA. Let me see what happens when I do that. All right, I've got 10 is equal to 7 plus, let me see, 30 over cosine 30 t, that's the VA, times sine 30 t, minus 32.2 over 2t squared. All right, these t's cancel out. That cosine 30 is a number, sine 30 is a number, 30 is a number. So that's just a number. 7, where's the number? 10 is a number. All those numbers to one side, solve for t. So I would get t is equal to 0.943 seconds. So that's the time that it takes to get from A to C. Plug this in over to my x equation, and then I could get VA. So plug in 0.943 right there. I can solve for VA, and I got VA is 36.73 feet per second. All right, so that is the initial velocity that we're going to have. This time right here is the time that it takes to go from A all the way to C. Okay, that was part of the equation, finding VA. All right, but I also wanted to find the height H that basketball player had to jump right there at B. All right, so now I'm going to do the same projectile problem. I'm going from A to B, knowing now VA. So I'm going to go from A to B. All right, so from A to B. Sometimes I like to rewrite everything in the x direction, rewrite everything in the y direction. I'm going to go ahead and start with my equation. I'm probably going to use SF equals SI plus VIT plus 1/2 AT squared. I'm going to use that for both directions. SF equals SI plus VIT plus 1/2 AT squared in the x direction. Now remember, I'm going from A to B, not A to C anymore. From A to B, yes, I started at 0, and I have an acceleration of 0, but I ended at 25 feet, and my V initial is VA, just found it, 36.73, but in the x direction it was VA cosine 30 times T. In that equation, there's only one unknown. I can go ahead and solve for that unknown, and I would get T is 0.786 seconds. And now over in the y direction, it started, so I'm going from A to B. It started at 7 feet, and it ended at H, which I don't know. I'm going to plug in H right there, equals 7 plus V initial. Remember, this is only in the y direction. So the V initial is that 36.73 sine 30 times T. Don't forget that T. And then plus 1/2 negative 32.2 T squared. And I already found the T. The T is 0.786. So plugging in 0.786 right there, then just doing the math, I would get H is equal to 11.5 feet. Kind of double check, does that make sense? If we go back up to the problem statement, let's see here. Yeah, started at 7, it ended at 10. Yeah, 11.5 I think makes sense. So that is our final answer, 11.5 feet. Okay, so this next problem. At the instant shown, bicyclist A is traveling at 7 meters per second as shown, while increasing speed at 0.5 meters per second squared. The bicyclist at B is traveling at 8.5 meters per second along the straightaway and increasing his speed at 0.7 meters per second. Determine the velocity and acceleration of A with respect to B at this instant. Express as Cartesian vectors. So I'm doing A with respect to B. Right. This is a relative motion problem. Velocity of A with respect to B and acceleration of A with respect to B. That is velocity of A with respect to B. And then also acceleration of A with respect to B. So it's a relative problem. And I'm going to need to do A slash B. So my first equation I'm going to write is VA is equal to VB plus VA slash B. That's kind of how I like to remember it and do these problems. Also, acceleration of A is equal to acceleration of B plus acceleration of A slash B. You may want to rewrite that as, VA slash B is equal to VA minus VB. Perfectly fine, but that's how I start mine. Okay, so I want to find VA slash B. Let me start with that one. So VA is equal to VB plus VA slash B. All right, so what is A? And another one of these things, this is real perceived. Okay, but I think this problem makes perfect sense. All right, velocity of A. The velocity of A is this 7 meters per second, but it is at that angle. I need to write that in I and J. All right, this is a vector equation. I need to write that in I and J. So it's 7 meters per second, but it is at some angle. All right, well, they don't really draw exactly that angle. They give me this 40-degree angle right here, and this vector is perpendicular to that 40-degree angle. So if I want a vector that is perpendicular to another vector, I kind of think about switching horizontal and vertical, or switching the x and y. All right, if this line right here is 40 degrees from horizontal, then his velocity vector is going to be 40 degrees from vertical. So this angle right here would be 40. So if that angle right there is 40, let me take that 7 and break it up into I and j. So his velocity should be, let me think about this, it would be 7 cosine would be in the y direction, and sine would be in the x direction. So 7 sine 40 in the I, and then it goes down 7 cosine 40 in the j. So that is my VA. Make sure you can do that. My VB is velocity of B. Oh, that's easy, 8.5, and it is in the I direction. Okay, plus VA slash B. All right. So that was it for this problem. Take this 8.5, subtract it over here, and you could get velocity of A slash B is negative 4I minus 5.36J. All your answers need units. These were all in meters per second. Okay, so that was the velocity of A slash B. Now let's think about acceleration of A slash B. Same method, right? We're going to write acceleration of A is equal to acceleration of B plus acceleration of A slash B, or A with respect to B. What is the acceleration of A? Acceleration of A. This is interesting. This is kind of a whole problem in itself. So let's think about and let's look at and write just this term right here. Let's find the acceleration of A. The acceleration of A. All right. Acceleration of that bicyclist A. The problem statement told me that he was increasing his speed at 0.5 meters per second squared. Right? He was increasing his speed at 0.5 meters per second squared. So he's speeding up. He's accelerating, right? These units even kind of, hint at acceleration. So he is accelerating, increasing his speed at 0.5 meters per second squared, and that is in the same direction as his velocity. So, I've got the velocity of 7 in that direction, but I also have acceleration of 0.5 meters per second squared in that direction also. So just like right here where I did 7 sine 40 in the I minus 7 cosine 40 in the j, I'm going to have some acceleration of A. He was increasing his speed, so he was accelerating at 0.5, and some of that was in the I, some of that was in the j, right? The 0.5 sine 40 in the I, and down 0.5 cosine 40 in the j. So that is his acceleration in A, but be careful, right? A is definitely traveling in a circular path. A is traveling in a circular path. A big hint was this 50 meters. It told me that radius, that was the radius curvature of the circular path that he is traveling in. So he also has this normal acceleration A in, and the normal acceleration is normal acceleration of v squared over rho. So he has a normal acceleration. So we're still just in this first term of the equation, haven't got to anything else. In the first term, we also have normal acceleration of 7. Let me kind of write this over here. AN is 7 squared over 50, and it is into the curve. It is into the curve, and it told me that was 40 degrees. I need to write this in I and J form, right? In order to use this relative acceleration equation, I need everything in I's and J's. So even this 7 squared over 50, I need that in I's and J's. And so this would end up being in the x direction. It would be cosine 40, in the y direction sine 40. So this also still has some acceleration of 7 squared over 50 cosine 40 in the negative I, and also down 7 squared over 50 times sine 40 in the j. So that is my acceleration that's my acceleration of A. And that's just the acceleration of A. That's just the first term. We also have to do acceleration of B in order to find acceleration of A slash B. All right, so I just did some of this math in blue. I like to go ahead and write out the decimals instead of rewriting all the sines and cosines. And so let me go back to my main equation, but plug in all of this 0.3214, 0.3214 I minus 0.383 J minus 0.751 I minus 0.630 J. So that was all just acceleration of A. The acceleration of B, if we go up, it said that B was also increasing his speed at 0.7 meters per second squared. So it has an acceleration, but that's easy. It's in a straight line, and all of it is in the x direction. So this would be plus 0.7 in the I, plus acceleration of A slash B, which is what we're really looking for. So then we would get acceleration of A slash B, or acceleration of A with respect to B. We should get negative 1.13 I minus 1.1 J. It has units meters per second squared. So that is the final answer for acceleration. Okay, so this one looks like a constrained motion problem, right? We've got two blocks that are connected by a pulley. Block B is moving downward with a velocity of 8 inches per second when SA is equal to 1 foot. Determine the velocity of block A at this instance. So block B is moving at 8 inches per second. Let's find the velocity of block A. Seems pretty easy. It also says H is 5 inches. Okay, so in a constrained motion problem, what I like to do, let's write the length of the rope. Let's write an equation for the length of the rope. All right, so we'll say L total. L total would be this length here plus this length here. I always want to measure the length of the rope from a fixed point outward. So I want to measure length from a fixed point outward. Let me start with this side over here. I'm going to measure the length of this rope from here outward, and let me call that length B, or L subscript B. L subscript B, I'm measuring it from a fixed point outward, and B, VB is in the direction VB is in the direction of LB, right? That's important, that the derivative is the velocity, and so we'll take the derivative of this LB, I get VB, and they are in the same direction. So the L total would be LB plus this length here. So remember that I cannot measure from here down. I can't call that LA. Why not? It is measured from a fixed point, but I need the velocity of A, right? Velocity of A is VA. It needs to be going in the direction of, the length of A. All right, so what am I going to do? I'm going to measure from here. I'm going to measure from here outward, right? From here outward, that's going to be LA, right? That's going to be LA because I'm measuring from a fixed point outward, and it's in the same direction as VA. So the length of the rope is not LA. The length of the rope is this hypotenuse, right? The length of the rope is the hypotenuse of this triangle. And this triangle has a base of LA and a height of 5 inches. So to get the hypotenuse of a triangle that has a length of LA, height of 5 inches, then the hypotenuse would be LA squared plus 5 inches squared, and take the square root. I think it's going to be easiest to write this to the 1/2 power. That's how I like to do that, because I know ahead of time I'm going to be taking the derivative of that. It's easier for me to take derivatives if it has a 1/2 power right there. Okay, so I wrote my length of the rope as an equation, and I'm going to take the derivative. The derivative of the length of the rope obviously is 0. The length of the rope is not changing in time, so its derivative is 0. The derivative of LB is just VB, and here's where it gets fun, taking the derivative of that thing inside of the 1/2 power. All right, taking the derivative of this whole thing raised to the 1/2 power. So anything raised to the 1/2 power, its derivative is 1/2 times whatever's inside, LA squared plus 5 squared. And then I subtract 1 from the exponent, so I've got a negative 1/2 power. But anything that's more complicated than just like an x, anything inside of the parentheses that is more complicated, I need to take its derivative, right? That's the chain rule. So I need to take its derivative. Well, derivative of LA squared plus 5 squared, derivative of 5 squared is 0. It's a constant. But the derivative of LA squared is, derivative of something squared would be 2 times that. And I need to take the chain rule again and take the derivative of what's inside of this parentheses. Right? I kind of have 2 big parentheses. I have this function that's raised to the 1/2 power. I'm taking its derivative, and inside the chain rule, I have this LA, which I have to take its derivative also. The derivative of LA is VA. All right, make sure you can do that, especially just make sure you can handle this problem of something that is a big square root. A squared plus b squared. Take the square root of that. Make sure you can take its derivative. All right. Why do I don't need to go ahead and plug in. I don't need to go ahead and plug in this LA is 12 inches. I don't need to plug it in up here before I take the derivative. I need to plug it in after I take the derivative because it is changing. All right, it's not a constant 12. If it was a constant 12, I could plug it in my first equation, and then the derivative would be 0. I need to wait, take the derivative, because it is changing in terms of time, with respect to time. So go ahead and take the derivative, and then plug in that this is 12 inches. Make sure your units are all consistent. The velocity of B is 8 inches per second. LA is 12 inches, and VA is the only unknown in that equation. So I've got 0 is equal to 8 plus 1/2, 12 squared plus 5 squared to the negative 1/2, right? Negative exponent just means take it in the denominator, times, right? There's no right here, there's no plus, no minus. This is this times this. So sometimes I leave too much of a space. Some people put in a plus right there. So times 2 times 12 times VA. And VA I can solve for. VA is negative 8.66 inches per second. Now, does it make sense that my velocity is negative 8.66 inches per second? Yes. I measured LA as positive out, and if B is going down, positive out, then A is actually going to be going in. So yes, it makes sense that our velocity is negative because it's going to be 8.66 inches per second to the right. All right, so here's a problem. Truck travels in a circular path having a radius of 50 meters. We notice that it gives us that. It tells us that. We're probably going to need to use that. It's traveling a circular path, so let's think normal and tangential. It has an initial speed of 4 meters per second. For a short distance from s equals 0, its speed is increased by v dot is equal to 0.05 seconds, meters per second squared. So it has some acceleration. Its speed is increased. That's its tangential acceleration. Let me go ahead and write that. Its AT is 0.05 s, where s is in meters. Determine its speed and the magnitude of its acceleration when it has moved s is equal to 10. All right, so its AT is 0.05 s. Its v initial is 4 meters per second. Determine its speed and the magnitude of its acceleration when it has moved s is equal to 10. So I want to know its v final at 10 meters at s is equal to 10. It started at 4 at s is equal to 0. I need to find the v final at s is equal to 10. Okay, so for these normal tangential problems, the tangential direction is really just kind of a 1D problem. The tangential acceleration is what we use for velocity, for finding anything in that tangential direction. So this is a problem where acceleration is given in terms of s. All right. It's not constant, right? Don't use one of those constant acceleration equations. Acceleration is given in terms of s, and I want to find v final. So let me look at my equation sheet. Here's my equation sheet. So acceleration in terms of s, and I want to find v. What do I use? Right here. Acceleration is in terms of s. I'm going to use integral v dv equals integral a ds. So integral v dv is equal to integral of a ds. Integral v dv equals integral a ds. So the integral, integral v dv, so plugging in a is 0.05 s ds. I'm going to take the integral of that. Integral of 0.05 s would be 0.05 s squared over 2. Right, this is s to the 1, so add 1 divided by the new exponent. But I need to evaluate this at s initial and s final. Then on the left-hand side, integral of v dv, don't do this too quickly, integral of v is v squared over 2, evaluated at v initial and v final. right, so VF squared over 2 minus V initial was 4. So minus 4 squared over 2 is equal to, so I'm curious, it starts at 0, and I want to see it ends at 10. So plugging in 0.05 times 10 squared over 2 minus 0, VF would be 4.58 meters per second. All right, so this velocity part of the problem, I just used tangential acceleration, and I just kind of thought, assumed and just thought of this as a one-dimensional problem like we did the very beginning of this semester. Okay, and that's fine for velocity. If acceleration is given in terms of a function, I need to take the derivative, take the integral, use tangential. I'm only thinking about velocity in the tangential direction. I don't have to use that normal just yet. But the second part of the problem, so I found its speed, determine its speed, found that. Now I need magnitude of its acceleration. Magnitude of its acceleration. So I need both, knowing that it's in a circular path, I need to find AT and I need to find AN. I'm going to start with AT. AT is, again, this is just sort of a 1D problem. Forgetting that it is traveling a circular path, let me find AT. Okay, and then kind of at the very end of the problem, I'm going to, tack on that AN because it's traveling in a circular path. So AT, it told me AT was 0.05 s. This is pretty easy. It told me AT is 0.05 times s. So if I want to know what is happening when s is equal to 10, plug in 10 right there, 0.5 meters per second squared, and that is in the tangential direction. All right, now AN is v squared over rho. And I found the v. If we hadn't found that yet, I would have needed to do this problem, even whether the problem statement asked for it or not. Would needed to have found VF. So this would be 4.58 squared over 50 meters was the rho. So this would be 0.42 meters per second squared into the curve, and so the magnitude would just be 0.5 squared plus 0.42 squared. Take the square root, magnitude would be 0.653 meters per second squared. So that is the sort of the magnitude of A. So this looks like a projectile problem. Golf ball is struck with a velocity of 80 feet per second as shown. Determine the distance d to where it will land. All right, so projectile problem. I'm going to kind of skip a lot of steps, and I'm going to look at the x direction. I'm going to look at the y direction. So in the x direction, let me kind of write what I know. Its velocity initial in x would be 80. All right, let me look at this. Let me think about this angle. I need to define my axes. I am going to define x as perfectly horizontal and y perfectly vertical. That's what I would do. I would not, some of you might be tempted to change your x and y to be along this incline. Why would that make it hard? It would make it hard because then the acceleration is not 100% in y and 0% in x. Then your acceleration would be part of it would be in x, part of it would be in y, and you would need to account for that. So I'm going to make, I'm not going to do this, I'm going to make x perfectly horizontal. So that means this 80, let's look carefully, this 80, it's 45 degrees to the incline, but then another 10 degrees, so I'm going to say 80 cosine 55 is the initial velocity. The acceleration is 0. It's s initial, and s final only in the x direction. Let me say it starts at 0 and it ends at, it doesn't really end at d. D is this hypotenuse, and so the x final would be d cosine 55. Right? No, sorry. Would be d, that 10-degree angle, d cosine 10 time, I don't know. In the y direction, the initial v in the y would be 80 sine 55. Acceleration would be, again, we're in feet, so negative 32.2 feet per second squared. And s initial and s final. Let's be consistent of y needs to be positive up. And I think I'm going to start at 0, so I'm calling this my 0 height. And so it ends up here at positive d sine 10, right? This height right here would be d sine 10, and that's where it ends up. All right, and t, I don't know. Let me take all of this and plug it into my equation. Probably this SF equals SI plus VIT plus 1/2 AT squared. I can use a constant acceleration equation because my acceleration is constant for both of these. SF equals SI plus VIT plus 1/2 AT squared. So D cosine 10 equals, it starts at 0, equals 80 cosine 55 t, and acceleration is 0. Two unknowns, but I'm going to write one in terms of the other. D would end up being 46.6. Would be 46.6. 0.6 t. D is 46.6 t, so that's about as far as I can go there. Now let me go to this other equation. SF is d sine 10 is equal to, starts at 0, starts at 80 sine 55 t plus 1/2 negative 32.2 t squared. So plug in this 46t right here. A little bit of math, and I would get 16.1 t squared minus 57.41 t is equal to 0. Factor out a t. 16.1 t minus 57.41 is equal to 0. So either t is equal to 0 or t from inside here, t is equal to 3.57 seconds. Plug this in right here. D is 166 feet. So here we have a constrained motion problem. You see a pulley that's connected, things are connected to. All right, so for the pulley system shown, each of the cables at A and B is given a velocity of 2 meters per second in the direction of the arrow. So we've got 2 meters per second this way, 2 meters per second this way. Determine the upward velocity of the load M. I like to kind of draw mine kind of connected right there. So that is the load M. All right, a constrained motion problem, I like to write the length of the rope. Write an equation for the length of the rope. Look carefully, and this is 2 ropes. This right here, 1 rope right there, and 1 rope right there. So I'm looking at the red rope. L total would be, all right, I need to, kind of define my lengths. I need to define it from a fixed point, and needs to be kind of be positive outward, and needs to be the length that I'm defining it needs to be in the same direction as the velocities. So here I'm going to make this my LB, and the derivative of that would be VB, and it's in that direction. Here I'm going to make this one LA, and its derivative, it's positive out, and its derivative would be velocity. And then I could have like in here LM, and also kind of looking at this pulley, let me call that pulley C. I'm going to have LC. Alright, so the red rope, the total length of the rope would be LB plus LM plus, alright, so this length from here to here, it's not LM, it's not LC, but it is the difference. LM, this would be LM, this would be LC, so that would be LM minus LC. So that's my equation for, let me rewrite that. L total is LB plus 2LM minus LC. That's my equation for that one. My equation for blue would be LA, so L total is LA plus, this would be 2LC. All right, that is this length LA, and then LC and LC. All right, so that's the equation for the total length. I can take the derivative of that and set the derivative equal to 0. So over here for the red rope, 0 equals VB plus 2VM, VB plus 2VM minus VC. For blue, 0 equals VA plus 2VC. So I know here that is VA, is that 2. This is VB. I'm looking for VM. So start with blue. 0 is equal to 2 plus 2VC. So I would get VC is equal to -1. And then plug this -1 in over here, and also know that VB is equal to 2. So 0 is equal to 2 plus 2VM minus -1. Be careful with the math. I would get VM is -1.5 meters per second. And that negative just means it is negative how I define my LM. Define my LM positive out, so LM is positive going down. So, VM would be 1.5 meters per second up. Okay, so I have a boat in the water. The water has a current. All right, so this is kind of like I like to think of this as a moving sidewalk type problem. It's going to be a relative motion problem. And remember, sort of for a relative motion, whether VA be boat, water, whatever, VA is equal to VB plus VA slash B. This is real, perceived, and that middle term is going to be the current. Okay. All right, so captain of a small ship capable of making a speed of 6 knots through still water, right? Capable of 6 knots through still water, desires to set a course which will take the boat due east from A to B, a distance of 10 nautical miles, to allow for a steady 2-knot current running northeast. So here, this current at 2 knots running northeast. Determine his necessary compass heading H, right? Where does he need to aim the boat? Measured from the north to the nearest degree. Also determine the time of the trip. We call it 1 knot is 1 nautical mile per hour. Okay, so we have our current is our water. So, thinking about this V A B A slash B, my V water is going to be right here, and we've got V boat, and so plus V boat with respect to the water right there, right? BW, BW. Alternate those subscripts. All right, so VB. This VB. I don't know its magnitude, but I do know that it is in the I direction. All right. Don't know its magnitude, but I do know it's in the I direction. Okay. VW. I do know its magnitude, 2 knots, and I do know it is at 45 degrees. V boat slash water. All right, so remember, going back up to a ship capable of making a speed of 6 knots through still water, that's not real, right? That's not really happening because we don't have still water. That's what he thinks it's capable of. So that's going to be, in this relative part of the problem. So this one, I do know its magnitude is 6, and its angle, that's what he thinks, his perceived, not what was really happening. So the angle that goes along with this is this heading H. I think instead of having that H, I think I'm going to measure below horizontal. So I'm going to say it's going at theta below horizontal. All right. So this is really 2 equations, the I equation and the J equation, and I can have 2 unknowns, and my 2 unknowns are VB and theta. All right, so let me kind of really write this. All right, so VB in the I direction is equal to 2 cosine 45I plus 2 sine 45J. That's the current, plus, all right, and so VB slash W is 6 at this theta, so 6 cosine theta I, and then down 6 sine theta J. All right, and so this is really 2 equations. When it's a little bit more difficult, I like to write I right here, write J right here. So the I components on the left-hand side, VB, on the right-hand side, 2 cosine 45, and then this 6 cosine theta. 1 equation, 2 unknowns. So let me jump to the J equation. The J equation, on the left-hand side of the equation, nothing. On the right-hand side, 2 sine 45, and then minus 6 sine theta. All right, so from this equation, I only have 1 unknown theta. So, subtract 6 sine theta to the left-hand side, divide through by 6, use inverse sine. You should be able to get theta is 13.6 degrees, and then plug this in up there and get VB is 7.24 miles per hour, or knots. All right, what did the problem really ask for? The problem really asked for the compass heading H. The compass heading H. Well, I found theta to be 13.6, so the compass heading H would be would make that plus 90 degrees, 103.6 degrees, so that is H. I also said determine the time of the trip. Well, I know that it is, that VB is real. It really is going at 7.24 miles per hour due east, and so if I know the constant, that's a constant velocity, nothing is changing. It's not accelerating or anything. Maybe you can say acceleration is 0. That's fine. But just really the definition of velocity is delta d over delta t. And so if this is average velocity or constant velocity. So here, 7.24 miles per hour would equal 10 miles. How many hours? What's the t that it would take? So we would get a time of 1.36 hours.